Hello everyone, welcome to the Routing Room, and today we're going to start a video series where we level up our knowledge on Cisco SDN. But before we jump into what SDN actually is, let's take a moment to review our traditional three-tier campus architecture. Now, if you recall with that, we have our access layer, distribution, and core layers. And what they do is that core layer is the high-speed backbone for the network. So its only function is to just be as fast as possible to transmit data from one point to the other as quickly as possible. Next, our distribution layer, which is where our policy enforcement primarily takes place. And finally, our access layer, which is our endpoint connectivity layer, which is where all those endpoint devices connect, such as our computers, our VoIP phones, IoT devices, if that's what's also in your network. Those things will connect at the access layer. Now with a traditional structure here, we have VLAN-based segmentation, which is kind of a security concern because we're only segmenting things based on their VLAN that they are placed in. We also have centralized default gateways, which typically occur at the distribution layer, and everything is managed at layer 2 by STP, or Spanning Tree Protocol. Now, there are some issues with that traditional campus design. Now, at the time when it was implemented, it actually was a great idea. But as modern networks expand and get more complex, those ideals that came around with that traditional architecture just don't really fit the bill anymore. So some of those issues are VLAN sprawl. So with VLANs, our IDs are limited to 4,096. And when we start talking about spanning those VLANs across buildings, across floors, or across departments, we're just not really setting ourselves up for success when it comes to scalability. Next, we have the dependency on Spanning Tree Protocol, which lowers our overall bandwidth because it has to place a port into a blocking state. That's just how it works. And then when switches are removed, replaced, or whatever, we also have delays caused by that STP convergence that has to happen when it rebuilds itself. We also open the door to issues with STP because we have to make sure those priorities and IDs are set properly so our root bridges and things of that nature don't get misconfigured when STP does its convergence. Our centralized default gateways cause inefficient routing and increased latency. And the reason this happens is because the traffic from two users who are on the same floor, on the same VLAN, same switch, has to go all the way up to that default gateway and then back down again. So we have some inefficiencies there with traffic management and routing. Even if those users are 20 feet apart, that traffic still has to route all the way up to wherever the default gateway location is and then all the way back down. Next, we have the issue of IPs being tied to a physical location, which means if a user moves, that's most likely going to require a VLAN change and then almost always going to require a change in an IP address too. And the issue with that is if that VLAN is quote unquote full, or if that DHCP reservation pool doesn't have enough space to accommodate that move, then that user is either unable to make the move or other configuration changes have to be made to increase the size of that DHCP pool or create a new VLAN. But the IP being tied to a physical location is definitely a problem that came along with that traditional campus design. Next, we have an issue with policy being based around the subnets or the IP addresses assigned to a particular VLAN. That causes some issues when we're talking about the least privilege principle. And it also causes issues with that entire IP address, an entire subnet being allowed or disallowed based on an ACL or based on some other form of policy. Next, we have large layer 2 failure domains, which means that if there is a broadcast storm or a routing loop, that's going to impact that entire VLAN segment. It's not going to impact just one or two users. It's going to cause degradation or a complete outage for an entire VLAN. And then finally, operationally, we have heavy scaling issues. So if we're talking about adding a new department, a whole new network, maybe it's for IoT or some other different type of network, or a whole new building, the complexity of adding additional VLANs, adding additional trunks, the IP address assignment, reservation pools, that is going to cause issues when we're looking at those legacy traditional design ideas. So the issue overall that we transition to when we're looking at modern networks, there's quite a few of them, but if we think about a traditional office area, user mobility is one of the largest issues, because if we have a user who's working on a project at his desk, he saves that to cloud, and now he has to get up from his desk and go present that in a different office area. Maybe it's to a different colleague, or it's to a group of people in a conference room. But either way, users are typically moving consistently across buildings, floors, or telework locations. That's one of the issues when we're talking about modern networking. We also have cloud and hybrid environments. Those applications for storage, for CAD softwares, for whatever software that the user is, whatever software that is being used at that time, those don't just live in the local data center anymore. They live in cloud environments. They live in Amazon AWS, or they live in Google Cloud or Microsoft Azure instance. They're not just local to that data center that sits in the building anymore. And then we have segmentation requirements. Security demands aren't what they were when we're looking at a traditional environment. Hackers are more sophisticated than they were, and a heightened security posture demands more segmentation than what we were given or what we've seen with the traditional architecture. And kind of to carry on with that, we have access expectations based on identity. So no matter what computer I sit at, and this is particularly important in a VDI environment, no matter where I sit, it shouldn't matter where I'm connecting from. It should matter who I am. So if I'm an administrator, I need to have access to those administrative tools and those administrative functions. But if I get up from that zero client or that soft client, somebody else sits down, they don't have those same, or they may not have those same access credentials that I have, even though we're sitting at the same desk, the same computer. It doesn't mean we need the same type of access that we had, or that each of us needs. It doesn't mean that we both get the same accesses. And then just efficiency from an operational standpoint. Manual configuration doesn't really scale very well. We're talking about opening the door to multiple user errors, because after all, we're all human, we all make mistakes. So if I forget to place a trunk on a port, or maybe I remove the entire trunk through a typo, now we're bringing down networks. Now we're causing issues to the customer, causing issues to clientele. So if we can automate configuration across a network, that will scale much better than having, a shop of people doing manual configuration changes across a variety of network platforms. And then as networks grow, we have more people doing more work. The networks are going to grow, and they're also going to become more distributed as the networks continue to expand and grow, and more protocols come into play. Telework becomes more of a thing, hybrid environments, cloud access. All of those things are going to cause networks to scale much larger and increase the complexity in networking. So now, what actually is software-defined networking, or SDN for short? Well, instead of configuring each device independently by a person, we have a controller like Cisco Catalyst Center that defines how the network should behave and will program those individual devices accordingly. Switches and routers continue forwarding traffic locally, but policy and configuration are driven by centralized intent. That intent is driven by administrators who specify that intent, and the controller translates that intent into device-level configurations. So basically, you, as the administrator, will tell the software controller, hey, I want the switch to be able to do XYZ. And the controller goes beep, boop, beep, 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 boop, 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 and spits out a configuration for that switch, router, firewall, whatever's being managed by the controller. So with that being said, the Cisco definition of SDN is an architecture designed to make a network more flexible and easier to manage. SDN centralizes management by abstracting the control plane from the data forwarding function in the discrete network services. So what all is built into SDN? Well, we have a centralized control plane. And what that does is that network intelligence is centralized in software. So where I was talking about Cisco Catalyst Center just a minute ago, that is the controller that will make the decisions for how devices are configured. We have a distributed data plane, but forwarding still occurs on network devices. We're not taking away routing. We're not taking away any functionality from the devices. They're just being configured in a different way. Intent-based policy goes back to the controller, where you as the administrator define what you want a device to do, and the controller will decide how to configure it to do what you want it to do. And then access decisions will be based on a user's identity and not only their location. Now, location can still be taken into account when we're determining access, but it is not the only way that we're going to determine the access that we're giving to an individual. And then last, we're talking about automation and consistency. If we automate the way that devices are configured, as things scale up and things get larger, we take away the potential for human error by allowing the controller to make the configuration decisions for us. We tell the controller, hey, we want to do this. And the controller will take that information from us and put it into a configuration for the switch, router, firewall, whatever, to receive and to be able to do the things that we as the administrators want it to do. So next, we're going to start getting into some of the pieces of a software-defined network. And first, we have the underlay. Now, what the underlay is it is the physical IP transport network. And what that means in an SDN environment is we have routed links or layer 3 links between all the network devices. So there's no more trunks or anything like that. It's all IP layer 3/30s/31s between network devices. The underlay provides layer 3 reachability between network devices, and it does that through those classic routing protocols, OSPF, ISIS, BGP in some instances, but it's going to use those traditional routing protocols to ensure that every single device that sits within the SDN fabric can reach every other device. SDN also has a concept called equal cost multipath, or ECMP, which means that unlike STP-based designs, a routed underlay allows for multiple paths to be simultaneously used for load balancing and resilience. So we're not having a link blocked because it's a redundant connection, only to be brought up later. If a link goes down, there's no convergence time or anything like that. Every link can be active, so you can have multiple pathways for a packet to get from point A to point B. The other important concept with the underlay is that it is both stable and predictable. The underlay, hopefully, is not going to be changing very often because it is supposed to be more simplistic and stable to reduce any kind of operational complexity. Because if the underlay has connectivity issues, then it's going to cause issues with other pieces of the SDN architecture, like the overlay. Now, the overlay is a virtual network that is built on top of the underlay. So it doesn't actually physically exist from a cabling standpoint, but what it does is it uses encapsulation to create logical layer 2 segments across the layer 3 network. Now, that encapsulation is typically going to be something called VXLAN, or Virtual Extensible Local Area Networks. And it uses VXLAN to encapsulate the traffic so that logical networks can span the actual routed fabric. The overlay is also what provides segmentation for us, and it does that no matter what the actual physical topology looks like. The users remain in the same logical segment no matter where they're located physically in a building or anywhere else. So even if you're at home and we're using some kind of VPN technology, to the overlay, it doesn't matter. You're still the same person that you were as if you were sitting in office. So the overlay has mechanisms to be able to perform that segmentation for you versus everyone else, no matter where you physically sit. The overlay also uses the control plane. The control plane is part of the overlay, and what that does is it tracks where endpoints live through a mechanism called Lisp. And what Lisp does is it maintains the mappings between endpoints and the switches, or fabric nodes is another word for the switches. Now, there are 3 planes when we're talking about software-defined networking. And logically, from top to bottom, we have the management plane first. And what the management plane does is it contains those centralized controllers that automate configuration, they push policies, and they provide visibility across the infrastructure. So something like Cisco Catalyst Center would sit in the management plane area. Next, we have the control plane, which determines where the endpoints are and also has protocols like VXLAN and Lisp. It maintains the mappings between endpoints and fabric nodes so that devices know where to send that encapsulated traffic. And lastly, we have the data plane, which simply just moves traffic. Switches and routers still forward packets locally. They also encapsulate that VXLAN traffic and enforce segmentation decisions at the edge. That is to say, at their own local switch. So, in summary, we have talked about a few things related to SDN. This is not going to be the end-all be-all. This is kind of a high-level look at what SDN actually is. So the things we've discussed in this video are, 1, traditional networks tie policy to location. So the access is only determined by IP address and the VLAN you're attached to. Those legacy campus designs couple segmentation and policy to physical topology, making mobility and scale much more operationally complex than what is needed in today's modern networks. SDN separates those responsibilities. The underlay, overlay, and all of those planes, management, control, data, they all have distinct roles. The underlay provides IP reachability, the overlay provides logical segmentation, and the management plane defines that intent that the administrators provide to the controller like Catalyst Center. The overlay abstracts physical topology. It provides logical segmentation independent of location. And I know we just talked about that, but I kind of want to hammer it home with the overlay doesn't care physically where an endpoint is in the topology. It provides that segmentation, that security segmentation, no matter where the switch is that the user is connected to, either from a wireless or wired standpoint. The overlay is also the foundation for VXLAN and Lisp. And the last thing is that policy is driven by identity. So we're making those authentication decisions based on identity metrics and not simply location metrics. And with that, that is the end of part 1 of Cisco SDN. And I will see you all next time.